Welcome to the course on FPGA-based signal processing systems. Today we'll be looking at the adaptive filtering. Adaptive filtering is a filtering theory which as a filter implementation, how can we use this filter adaptively to remove certain noise from the accurate signal or the disturbances from the signal, or the signal and the noise is correlated or not. These concepts we'll be learning, and what are the mechanism in which this filtering can be done. One of the basics of the adaptive filtering theory is Wiener filter. So I'll first look at the Wiener filter, and then we'll move on to the what are the different types of adaptive filtering, or what are the algorithms used in the adaptive filtering. The Wiener filter, which is shown over here, has the block diagram can be represented in that, the filter how it is used. So the desired signal, let us say this is D of n, and the input signal is X of n. Okay, so the inputs, and you can look at the block which has the FIR filter. Very happy about this filter that we have learned already what is the filter structure and the what is the coefficient in FIR, or what are the coefficients, feed forward coefficients of FIR, how to get those coefficients, and how to design that filter, and so on. So knowing that those coefficients, now we are referring as a weights W1, W0, W2 and Wn minus 1. So this varies from W0 to Wn minus 1, depends on the tap of the filter or the order of the filter. So these weights, first suppose we say that it is fixed, and there is an input signal and there is a desired signal. So the desired signal, suppose a sine wave here, and for the input signal what I am getting is sine wave plus noise. Okay, so this filter gets something, filter out certain things, that is noise, and then give the sine wave only here. And if you subtract these two, the error would be 0. So this error at a first instance cannot be 0. So the error can be taken and update that error for instant wise. Suppose at the nth instant what should be the error, and at the n plus 1th instant what should the error to be used to correct these weights. Because the weights are fixed, or the coefficients suppose are fixed, then whatever the given input, the output would also be fixed, right? So in that case, so if can we change these weights through some mechanism? That's what the adaptive filtering does. So this is a filter which we make it adaptive by making it the weights adjustable, so that keep adjusting these weights so that the error becomes 0. Till this feedback can be done up to the error making this error to 0. So in this case, that you can see this X of n is the input, and Y of n is related with W transpose, which is W the weight vector, and X of n weight vector. What we mean here is the coefficients of the filter. X of n is the input, D of n is the desired signal, E of n is the error. So this is the basis of this Wiener filter. So if we take this, what does it do? Find the impulse response of the coefficients, or impulse response coefficients of this filter, so that the expected value of the squared error is minimized. So let's see this, what is the meaning of this E square n, and so on. So now we take the two categories, as we said, this is the desired signal in the previous case, that input signal is X of n, and adaptive filter which can be an FIR filter, and we get Y of n out of it. This filter needs the coefficient to be adjusted, and we get the error E, and put it to an adaptive algorithm where it updates the weights of this filter then and there. So whenever this is getting the every instant or iteration we call it. So in each iteration it calls the E of n, and the E of n is used in this algorithm, and then output gives the weights which needs to be put up in the adaptive filter. So if we keep doing that, this error to be minimized to error that is expectation of the squared error to be minimized, or the sum of this squared errors to be minimized, depends on this adaptive algorithm will be. So now this is one way that in this adaptive algorithm is used. So if you don't have this adaptive, then it is that is a FIR filter simply, but when we make it adaptive in the sense that we have this weights to be updated every iteration. And if we see this adaptive filtering can also be used in system identification. For example, this is the input signal which needs to be given to the unknown system. The system is not known, right? So in adaptive filter which is used over here, and the input X of n is given to both, and unknown system would give an output depends on the input, and the filter also gives certain output. So if we take the one, subtract one from the other and get the error, and this error gets updated and again adjust the filter coefficients, keep doing this until this unknown system mimics this filter, so that the error becomes minimized or zero. So this is how then once the error is minimized, then we can say this filter, this is not the unknown system, is nothing but this. So this way this unknown system can be identified. The adaptive filtering can be used in system identification. So in these types of adaptive filtering, there are two types of objective function, how the error to be made zero or minimized here. One is that we can have this objective function or the cost function to be e square n, that is expectation of e square n. E of n is the error and square it, and then expectation of that to be minimized. That is one objective, that is expectation of instantaneous squared error. That is one cost function that's to be minimized. Or the second category of objective function can be e square I, which is actually summing up the squared error, squared e square I from the up to the present sample. So I equal to 0 to n, what was the previous, I equal to 0, e square 0, and then I equal to 1, e square 1. So summing up e square, that is error squared error up to nth sample, and try to minimize that as a cost function. So there are two categories. So depends on that this mean square algorithms and then least square algorithms are possible in using the objective functions. So with this background, the Wiener filter which we have taken is going to be the y of n. If you go back to this cycle, the x of n is given and the FA of filter output, we assume that is W naught is the weight of the FIR, that is weights, we say weight vector, W naught, W1, W2 up to Wn minus 1, and this is x of n minus 1, x of n minus 2, and up to n minus n samples. So these are input samples given to the adaptive filter. Okay. So far considering the Wiener, that's not adaptive, and let's see the how to make this adaptive also. So the W of n and the x of n can be written as W transpose x of n. This is W naught, W1, W2 up to Wn minus 1 is a coefficient. When we say weights, you need to recall that FIR filter coefficients. That W naught, W1, W2, Wn minus 1, which is a weight, it's a constant, and it would be updated for every instant in the adaptive scheme. So right now this is the weight which is constant. W transpose is a vector, it's not depending on anything, that's only the tap of, depends on the size that weight vector would be. W transpose x of n, this can be written like that. So where W transpose is W naught up to Wn minus 1, and xn is this xn minus 1, and so on. So we have W naught and then xn transpose. So if you multiply that, you will get the y of n. So from this, the function to be minimized or the objective function, what is the function here? So we have this d of n, desired signal, which is coming in one line, and the x of n, which is multiplied, or x of n samples, the input samples are multiplied with the weight vector and getting y of n. So d of n minus y of n is this error we have seen in the diagram, d of n minus y of n, and its square, the expectation of this. Okay, so we have to minimize this objective function. The objective function is depending on the weight to be, it's a function of weights. So expectation of e square n, it's dn minus yn the whole square. So if we expand this square, so expectation of d square a minus b the whole square, so 2 dn yn minus plus y square n. So expectation of all this is, let's simplify that. So this objective function, and what is this y of n now? So y of n is W transpose x of n, which we got it from the filter output, and that's the output signal of the filter, and square, find the square as well. So the y of n can be written, because this is a vector, y of n into y of n transpose. So if we have this W transpose xn and its transpose, so what we get is AB transpose, B transpose, and A transpose. So the same way, so W transpose x of n, and here is x transpose W. So we get y square n. So substitute them, JW here, d square n, 2 d of n is here the expectation is taken inside, and d of n, y of n is w transpose x of n, which is substituted over here, and expectation of y square n, whereas we got here w transpose x of n from here. Okay. So for the filter coefficients, w here, which is not random variable, I said for a first one iteration it is constant, so we consider that w is not a random variable. We can take this out here in the equation, so this retained as such, and then 2 into w transpose is taken over here, and expectation of d of n x of n, right, and then here we have this again, the w transpose over here, which is not the, which doesn't have this expectation of x of n and x transpose and w. So taking out of this expectation w and w transpose and w. So from this simplification, what we can say, this is desired signal, that is it is zero mean. Okay, the assumption you can see. So if it is zero mean, the desired signal is zero mean, then this d square, this is the signal square, and its expectation is going to be the variance sigma d square. So variance of d of n. So this can be simplified to sigma d square, and let's take, so this function now reduces to here. This function is reduces to d square. Okay. And we call, we'll also decide what are these d of n, expectation of d of n x of n, and the expectation of x of n into x of n transpose. So in the cost function now, let us decide the second term is p, is the cross correlation between the input and the desired signal. Okay, so we term this function as p, okay, small p, that is going to be the cross correlation matrix, and then have this self correlation, or xn and xn transpose. This the signal itself, x of n is the signal, input signal, from which we are going to remove the unwanted signal. So x of n correlating with this x transpose x itself, it's a correlation matrix. So p and r will be used throughout this algorithm, the developing the adaptive algorithm. So we can identify from this cost function, this is going to be the cross correlation function, and this is the autocorrelation function. So here is the R, which we have given expectation of xn transpose, in which this is what we have considered is a real signal. So if it's a complex x of n, then that's going to be a symbol which is the cross is transpose complex conjugate. This is going to be a complex transpose and complex conjugate. So considered here we have transpose only because it's a real signal, so it's not having any conjugate here. So the objective function now reduces to, so sigma d square, this term has now turned to sigma d square, that's a variance, to w transpose, and this is p over here from this, and w transpose, and this is going to be r and w. So now the equation now reduces to, the cost function reduces to sigma d square to w transpose p and w transpose r w. So from this, the second term which is linear in terms of filter coefficients, so we don't have any other terms here, this is w transpose here, but here if you see w transpose r w, that term is quadratic, so it's not linear. So this is third term is quadratic, w transpose r w. So the objective function is now quadratic function, and it is also convex. Okay. So now the objective function, from this we have to find the solution for the optimum solution according to the Wiener. So this has a unique minimum point. Anyway, if we have this quadratic function which is having the minimum point, unique point, which can be computed by taking the gradient of this j, the cost function with respect to w, and then equating the gradient to 0, we'll get the optimum solution. So we will take this equation, and instead of n taps, we'll reduce this for understanding the n taps to 2 taps, and then try the cost function, how it is going to be, how take the gradient, and what is the solution of this Wiener. So considering 2 tap filter, here w transpose now, not n vectors in the weight, maybe as a weight vectors, w naught and w1 are the just 2 taps in the FR filter, and then x is the samples, also input samples xn and xn minus 1 to be considered. And so the correlation matrix xn transpose, if I multiply, it will have 4 terms here, r of 0, R of 1, R1, the diagonals are zeros, and the half diagonal R1 and R1. So from this we have the equation, the cost function. Now let us substitute this here, and P and W transpose R and so on. So here 2 and W transpose is W naught and W1. P becomes that P of 0 and P of 1, which is the cross correlation of Xn and Dn. So you'll have one at 0 and one at 1. So we have two terms in this. Again, the W transpose is this, and W is going to be that, and R as we have seen. So if you multiply them all, so we get sigma d square, and 2 into W P naught, the other term W1 P1, and W naught R naught, and W1 here R1. Okay, this one will have 1. This is 1 again, W naught R1 and W1 R naught. So if we simplify this, these two terms here, so that's just a multiplication. So we get W naught square R naught and W1 square R naught, and 2 W naught W1 R of 1. So which is from here. So we have one term here and the other term also, so multiplied. So these four terms are combined now, getting 3 terms, and other for W P naught and P of 1. So this cost function, now find the gradient of it with respect to W. So for one weight vector is W naught, so differentiate it with respect to dou J by dou W naught, minus 2 V of naught 2 W naught R naught to W1. So here if you see, this is going to be 0, and this term exists, and this won't be there because there is no W naught, and here 2 into W naught R naught, this term exists, and here this term exists and this doesn't. So that's how this differentiating this would cost. So if we differentiate it with respect to partial differentiation with respect to W1 here, dj by dou W1 results in this term doesn't exist, and this would be coming as here, and this term won't be there, and the 2 W naught R1, and here is 2 W1 R naught. So taking this gradient and then equating to 0, so this is del j, we call this as del j, this vector which is going to be dou j by dou W naught and dou j by dou W1. So this is here equal to minus 2, we put it in the matrix form, P naught P1 plus 2, that is 1 2 3 4, this is 2 by 2 matrix into W naught by W1. So this we know, the P naught and P1 are P, and R is this 2 R W. So what we have, this gradient is minus 2P plus 2R W equal to 0. So if we equate this, 2R W equal to 2P, and then 2 gets cancelled, here W is equal to R inverse P. So we get it from this equation. This is the optimum solution of the Wiener. So if we have this, if we know the autocorrelation of the input signal, autocorrelation matrix, and the cross correlation of the desired signal and the input signal, cross correlation matrix, then take the inverse of the autocorrelation matrix into the cross correlation matrix, and that should be the weight of the optimum weight which can give the error minimum here. So this is the way the Wiener works. So here we have just decided one stage W what is the optimum W here. So from this Wiener, how to make the Wiener optimum solution is this R inverse P, and so computation of this R inverse is becoming intensive, that is autocorrelation matrix, and moreover these R and P are not available when you that must be estimated from the desired signal and the input signal here, the relation between them. So if you take this J function, that is W with respect to W naught and W1, we had this only 2 filter, and that function lies like this. The minimum can be obtained here, and if you plot it W naught W1 and J of W naught W1, so you will have this convex function which has the minimum somewhere here, that's a unique point, and which is, you can, from this you can get the W naught optimum value and W1 optimum value also, just a representation of this cost function, the convex function which can where the error can be minimum, can be picked up from the plot. So now based on this Wiener solution, the optimum solution can be, what is the gradient search. So these gradient search and the steepest descent are the basis for the least mean square algorithms. So how this in few steps how the gradient search can be done to the get this minimum solution. So the cost function GW and the weight vector W and an estimate of the weight of the n sample or W of n. Now you can see that W is now is a function of n. So how to update this vector W? So in the previous case in the Wiener we did not update that vector. So how do we update that vector weight vector here? So W of n plus 1 equal to W of n plus G of n. So the W of n is at the nth iteration and the present, and the next iteration how this weight vector needs to be updated. So this is G of n is the gradient we use this direction in which it should move. So the Wn should be updated in such a way that lead to the error minimum. So this is called the direction vector. So the weight vector is updated with the present one. The next weight vector should be equal to present weight vector plus the direction vector in this gradient. So we are searching that where this would be which can lead to the minimum. So the G of n now if we have this cost function is W of n plus 1 and J is W of n, G of n, which is to be minimum. Now the cost function is now changed to J of W to J of n plus 1 minimum. So from this, using the Taylor series, actually if you have function x naught plus del x, so f of x naught plus del x by 1 factorial into f dash of x naught plus del x square by 2 factorial f double dash and of x naught del x cube by 3 factorial into. So this is the Taylor series, using the Taylor series over here in our cost function now, which has the direction vector as well. W plus G is added. So the expansion of this f of J W and del x over here is G, okay, and the f dash corresponds to J dou J by dou JW by WI, and double dash corresponds to this and triple dash and so on. So here you have the del x square GI and GJ. So G is for every I values it will be varying. So there should be a summation here which is not shown over in the case. So we'll have the different weights. So that is what the summation will be. So it is expanded through the Taylor series. So considering this two tap for simplicity of and using the Taylor series, how this can be reduced. So W plus J, where JW and this is going to be G naught and G1 only. There are two G values. So G naught is 1 and G1 is here. The first is with respect to 0 and the second with respect to W1. So we have this function getting over here, and then half into the summation G naught square when both I are same 0 1 0 0. So d square JW by this, and G naught G1 and J is made 0 1 here. So similarly, so W1 J would become 1, and then make I equal to 1 and J 0, and the combination of 0 and 1, 0 0 0 1 1 0 and 1 1 here. So G1 1 square here, I and J are 1. Dou square JW DW1. So the expansion of this cost function now for the two tap filter. So differentiate this with respect to W now here, and then so dou W by dou G naught actually here. So J by will have with respect to W naught, G naught, and then G1 here. So and then differentiate this with respect to G1. We have so this weight vector is differentiated with respect to G. Okay, so G and G naught. So we have the W naught from this case. So JW, and then with respect to G naught, this term would exist, and then this term would exist, this term and this term, and then this won't be there and this won't be there. So similarly, when we differentiate it with respect to G1, and these two terms will not be there, G1 1 2, and then this term. So likewise we have this G, the differentiation with respect to G. So we have the whole thing, but each one was with the one already we have is W1 in the Taylor series. So we get this equation for by differentiating this with respect to G, and then take the matrix. So this is del J into Wj by G naught and G1. Consider this as a matrix in which the del J will have 1 2, this 2 2 1, two of them, and then remaining this 4 to be considered in one of the as a matrix. So if you write these two equations in a matrix form, so del J with this the gradient what we have already got, if you recall from the Wiener solution, that is del J, this is here, and you have this 4 of them, G0 G1 multiplied here. So this matrix in the gradient search to find G, so equate this to 0. So we differentiated the cost function which has the direction vector, equate it to 0. So this one is called the Hessian matrix. So del J, and this is now replaced as H, G equal to 0. So del J equal to minus H minus this, if we minus Hg, so where we have this G, need to find H inverse minus H inverse del J. So if you know the inverse of this and the gradient vector which we have, this del J, the direction can be found. So the update equation, how does it change? That now the W of n plus 1 equal to Wn plus G of n. So now gets into G of n is now substituted over here, H inverse del J. So from this is the Newton's equation actually, if the gradient search. So this H, if we substitute this, the R, that's the autocorrelation matrix R, H equal to, if we substitute 2R, and the del J, which we got it from the Wiener, minus 2p plus 2rw. You substitute these things and you will Newton's algorithm convergence to the optimum solution in one step, that is W of n plus 1 equal to just R inverse p. So this would converge if we have this substituted in this case. Okay, so these two conditions, if you substitute this, you have this. So gradient search leads to the optimum solution of Wiener, R inverse p in one step is possible with H and del J as this. So we have in the gradient search, we have by finding the G, the direction in which it should the weight vector needs to be updated. So the steepest descent, similarly we have the equation in the Newton's equation, H instead of having 2R in the gradient search. So where the descent would be steepest, we keep going in this direction. H is equal to 2I, the identity matrix. If the update equation now, H is replaced with 2I, then it is going to be 1 by 2 del J. I is the identity matrix, and there is a constant mu which is added over here, which is greater than 0, and that is called the rate of convergence. So depends on mu, the weight vector will be updated, and the weight vector we can find the solution also. And if mu is actually the constant rate of convergence, how fast the convergence can be, how fast we can find the we can converge to the optimum solution here. So del J from the Wiener minus 2p 2rw, and if we substitute here this del J minus 2p 2rw, so we have minus mu to cancel p minus rw of n. So this is the equation, the steepest descent. So we further reduce this to get the update equation. So the steepest descent algorithm, where we initialize this weight vectors initially to 0, W of 0 is 0, and n varying from 0 to 1. How do we do this algorithm as a updation? Okay, so W of n plus 1 equal to W of n plus mu into p minus rwn. So where R is the autocorrelation matrix and this is the cross correlation matrix. So if we know P and R, so the weight vector can be updated. This is giving the convergence, rate of convergence. So if mu is more, so what is the condition on mu? Mu should be between 0 to lambda max, where lambda is the largest eigenvalue of R. If the R matrix is known, then it would be the largest value. So mu can be fixed in between this. So if mu is larger, so the algorithm take larger steps to converge. larger steps in the sense that the step size will be more, and then it would quickly converge, but there may be errors. So if you choose mu small, it will take more steps to converge, and then the error would be less. So the way in which the solution is obtained, which depends on the mu, so that is called the rate of convergence. So this needs to be updated, or this needs to be programmed in the to put it in the FPGA. So the weight vector needs to be updated in this fashion in the steepest descent. So we will be looking at the LMS algorithm. Now the least mean square algorithm, in which how this steepest descent can be used. So that is a steepest descent algorithm. We have this update vector, in which the approximate version of that steepest descent is the least mean square algorithm. So let's take this W of n plus 1, W of n. So mu p minus r w n. This is the update equation for the steepest descent. So if we approximate this p and r, because this is not known, as we said in the computation of is a inverse in one case, and we moved to the gradient search and then found the steepest descent. So these are not known in the real time applications. So what was this R definition? R is expectation of the x of n and x of n transpose. Instead of having this expectation of it, just take the x of n and its transpose, approximate it this way. Similarly, P, instead of having the expectation approximated, this is just a multiplication of D and X, that is said signal and the input signal, and the matrix. These are the cross correlation matrix and the autocorrelation matrices are now reduced to this form. Then update equation, now simply we can change it like P is now D of n x of n, and R is x of n x n transpose. So in that case, how that's what we are doing in this LMS. So taking this x of n common, D of n minus x of x transpose W. So which is here again x of n into this is y of n. So we know this is going to be y of n, the FF filter output we saw, and this equation now reduces to E of n. So this is the LMS equation. So you compute the error and update the weight vectors. So the algorithm now initialize this the steepest descent, how it is changed to this LMS. So it's an approximate version. LMS is the approximate version of the steepest descent. So the y of n is known, W transpose x of n, we fix it initially 0 and compute E of n for every n values. Okay, D desired one is known, and then y of n we are computing from here, subtract them, get error, and put that in the update equation. Mu should be fixed as mu needs to be fixed as 2 by lambda max, between 0 and 2 by lambda max, where lambda max is the maximum eigenvalue of the R, the autocorrelation matrix. So E of n into x of n, this is how this weight vector is getting updated in the least mean square error. So this minimizes the mean square error, and these are coming under the mean square algorithm. The cost function which when we started, we have these two types of cost function. This is coming into the mean square algorithm. So the LMS computational complexity, if we take step by step, to compute y for an n-tap configuration of the filter, it takes multiplication n multiplication and n minus 1 additions to compute this alone, and to error there is only one addition. And the update equation itself is taking this n plus 1 multiplication and n additions over here. Okay, so to add all the multiplications, we have 2n plus 1 multiplication, and addition is 2n. Okay, so if you sum it up, this is going to be 2n additions. So the order is n here, 2n plus 1 and 2n. So this is important to when we implement it in the DSPs, FPGA or DSP processes. So coming to the convergence, so the certain assumptions are used. X1, Xn, the input signal are statistically independent of each other, the samples, and the weight vector is independent of x of n. Okay, so the input vector, these are the assumptions used in the calculation, and the input vector x of n is independent of the previous samples, x of n and dn minus 1, dn minus 2. So these are independent. They are not correlated. That's what we're trying to say, I mean very independent one here. So this speeds up the convergence and of the LMS. So we have seen the filter, adaptive filtering concepts starting from the Wiener filter, gradient search, algorithm, how the direction has to be added with that. Also the steepest descent, what is the update equation. So from this update equation of the steepest descent, we have derived the update equation for the LMS, least mean square. So these algorithms can be coded and then put in the FPGA for testing the signal processing or removing the noise or whatever the signal content which is not required from the input signal. So that depends on the desired signal. So we'll look at the recursive least square algorithm as well in the adaptive filtering in the next lecture. Thank you.